Hey y'all, it's Dr. Know-It-All. Today I want to talk to you about a paper that is making waves around the interwebs right now. It's called Darwin Gödel Machine, Open-Ended Evolution of Self-Improving Agents. You can see that one of the authors is from Sakana AI, which is famous for the research scientist, etc. Then you've got UBC, and you've got Canadian CFAR and the Vector Institute, which I don't know where that's actually out of, but it looks like it's kind of a Canadian type of paper. This is a big deal because this actually opens the door to self-improving, e.g. self-accelerating AI, but I want to put a little bit of a brakes on it because as I made a note here, and you'll see a lot of active reading here, I geeked out about this paper. Really cool. But I said, this is like step one in a 10,000 step journey. So many possibilities, and this is such a small step. So it's a very small step at this point. It uses one of my favorite AI techniques that I used back when I was a student, which is genetic algorithms, kind of, sort of. I mean, it's in that same vein, but it does it very differently. But I've always been an evolutionary AI kind of person. Neural networks and genetic algorithms were the two things that I particularly loved when I was in school. And that was back in the Stone Ages in the mid-20 teens, when neural networks in particular were still kind of poo-pooed. A lot of the older faculty said they weren't as good as a lot of the older techniques because they had been tried in the 80s and they hadn't come up, they'd come up wanting, basically. Anyway, I did my master's thesis on neural networks, and haha, I think I won, because I think neural networks have clearly become quite the golden child. But the big part about this is that this is a really cool paper, but there are reasons why this is not quite as amazing as people think. It opens up the possibilities for that, but it's not there yet. Anyway, this is from the 29th of May, which is just a few days ago. And the big thing I want you to read through this entire paper with is actually way down here in the conclusions and limitations, which is, note this, it takes about 2 weeks and incurs significant API costs. In other words, it costs a lot of money to run this, to do one of these evolutionary experiments. So that's the big thing to keep in mind while reading this, is that while this is really an amazing first step, it's not something that you can do at scale quite yet. Too expensive, both in terms of cost and in terms of time. But it really kind of points the way. It's pointing a finger at the direction that things can be going. And that also entails a little bit of scariness, because like when you get self-improving AI, it could actually kind of escape. And they talk about safety towards the end of this. Anyway, let's go ahead and read the abstract here. Most of today's AI systems are constrained by human-designed fixed architectures and cannot autonomously and continuously improve themselves. Very true. The scientific method, on the other hand, so that's one thing. We've got the scientific method, and the other part is going to be Darwinian evolution. The scientific method, on the other hand, provides a cumulative and open-ended system where each innovation builds upon previous artifacts. That's the important part about this, enabling future discoveries. There is growing hope that the current manual process of advancing AI could itself be automated. If done safely, big point here, such automation would accelerate AI development and allow us to reap its benefits much sooner. This prospect raises the question of how AI systems can endlessly improve themselves while getting better at solving relevant problems. Previous approaches such as meta-learning provide a toolset for automating the discovery of novel algorithms, but are limited by the human design of a suitable search space and first-order improvements. In other words, it's tethered to humans. We have to come up with these new concepts and everything, and therefore it's limited by, the speed of human beings. The Gödel machine, on the other hand, and this is something that was introduced back in 2007, it's a more of a theoretical kind of paper, introduced a theoretical approach to a self-improving AI capable of modifying itself in a provably beneficial manner. So that's the big thing, is there was a logical sort of mathematical proof that it was making improvements. That was the Gödel machine. Unfortunately, this original formulation is in practice impossible to create due to the inability to prove the impact of most self-modifications. So, you can kind of think through that and it makes perfect sense. To address this limitation, we propose the Darwin Gödel Machine, or the DGM, a novel self-improving system that iteratively modifies its own code, thereby also improving its ability to modify its own code base and empirically validates each change using coding benchmarks. In this paper, the DGM aims to optimize the design of coding agents powered by frozen foundation models. So in other words, they're using Claude Sonnet for most of this, and they're just taking Claude Sonnet as it is. The foundation model, or FM as they call it throughout the rest of the paper, is is just an entity. So what they're doing is they're changing the tools, the access that it has. So what's available to this agent is not modifying its own sort of brain, but all of the tools around it. It's able to rebuild the tools. If you imagine it was like a person agent, right? Like a human being, it could modify the tools it could use. It could make new hammers. It could make new saws. It could make new whatever you want to talk about, right? It could make those new tools, but it can't change its own internal brain. And the authors talk about how that's something for future work, but given the fact that this is so expensive and so time consuming just as it is, it begs the question of how you would do that in a cost-effective and time-effective manner. Anyway, in this paper, the DGM aims to optimize the design of coding agents powered by frozen foundation models, which enable the ability to read, write, and execute code via tool use. Inspired by biological evolution, so there's Darwin, and open-endedness research, which is basically the scientific method of building upon previous discoveries, the DGM maintains an archive of generated coding agents. In other words, when it creates a new agent, a new tool, a new redo of the code, it saves that rather than throwing it away with a Darwinian filter that cuts off ones that don't behave in a good enough manner. So that is a question of what is good enough, and do they have the bar set correctly? That's an interesting question for this. Anyway, the agent then samples from this archive and tries to create new, interesting, improved version of the sampled agent. This open-ended exploration forms a growing tree. So imagine one agent, two agents, or four agents, and 8 agents, and 16 agents, right? So it gets bigger and bigger and bigger. It forms a growing tree of diverse, high-quality agents and allows the parallel exploration of many different paths through the search space. Empirically, the DGM automatically improves its coding capabilities, e.g. better code editing tools, long context window management, peer-to-peer review mechanisms, producing performance increases on SWE-bench from 20% to 50%, that's pretty huge, and on Polyglot from 14.2% to 30.7%. So these are big improvements here. Furthermore, the DGM significantly outperforms baselines without self-improvement or open-ended exploration. All experiments were done with safety precautions, which they will discuss later, e.g. sandboxing, human oversight, etc. Overall, the DGM represents a significant step towards self-improving AI, capable of gathering its own stepping stones along a path that unfolds into endless innovation. All code is open sourced at this thing, and of course I will leave a link to this paper in the description so you can read it. There is a huge appendix. I think it's somewhere on the order of 55 pages or something is the appendix, so you can read through a lot of examples if you're interested. All right, I'm going to try to go through the rest of this paper as quickly as I can. I really geeked out on this paper, so it was difficult. This is called active reading. I was very much involved in the reading process here. They start with the scientific process, which is based on building upon artifacts that other people have discovered, basically, right? So you could think about, something like this iPhone is the result of millennia of materials research, and in the last 100 years or so, quantum mechanics, and then software development, and all of these kinds of things. All of this stuff builds and builds and builds, and so every new discovery is kind of a building upon a previous discovery. That's the important part here. And that's what they pull from to create the DGM here, which is that it takes a previous artifact, in other words, a being. So imagine me having a child or something, and then the evolutionary mode steps in. It's like, is this child good enough to survive in the world and thrive? If not, then unfortunately they go by the way of the dodo or something, right? But if they do, then they're available to reproduce and create a new generation after them. That's that kind of a thing. So it's the combination of the scientific method of building upon previous discoveries and Darwinian evolution, which is filtering things out if they're not good enough, but also allowing something that looks suboptimal at that particular moment to continue to exist. In other words, it doesn't have to be the best model at any given stage. It could be like okay, but not great. But what you can see, and we'll see this in a graph in a little bit, is that something that performs below the best model at a certain generation actually improves. That discovery was actually more important than you might have thought at the beginning, and it therefore allows improvement later on. And that's where the genetic algorithm sort of antecedent comes in. It's that ability of the agent to create a population of possibilities and sample from that population so that you're not always just looking at the best possible solution at any given moment, because that could lead to a local minimum. It could just settle into a local minimum instead of finding the true minimum in a search space, and that is the best answer, right? So this is very important to this methodology. It's somewhat similar to simulated annealing if you're used to that sort of thing. But again, genetic algorithms, you take populations, you pull the best ones out, but there is a probability that a suboptimal population member, right, an entity here, could be selected for breeding into the next generation, which allows something that doesn't look like it's doing the best at a given moment to rise to the top. So that's the really important insight here in this paper. So here we have a graphic that's kind of an outline of how this works. You have a parent at any given generation, and it actually only starts with one agent, which I find a little disappointing. I wish it started with a population rather than a single one, but I'll talk about that more in just a second. Anyway, it starts with a parent. The parent is able to self-modify its tools that it uses. It then is evaluated on SWE-bench or polyglot. So they only got 2 evaluations at this point, but it's evaluated on that. First of all, does it compile? Is it able to run? If not, it's filtered out. It's kicked out of the next generation. If it is able to compile and run, it's evaluated on the benchmark, and then it's placed into the child generation with a probability of being reproduced in the generation after that based on the evaluation in the benchmark. So in other words, the parent goes and it modifies itself. So right, this is its own tools. It's given very few tools at the beginning. It's just basically able to run a bash command and modify files. So it's not able to do all that much, but it's able to modify its code. So change those tools, add new tools if it wants, whatever it does, but it modifies that code, assuming that it's able to run in the next generation. In other words, it's able to thrive, I guess that's the filter, the bar. And it took them way deep into the paper to actually get to that. I was like, come on guys, tell me what the filter is. What is the Darwinian filter? They should have kind of front loaded that. Also, they should have front loaded the expense of it as well. So I find it a little disappointing. The paper overall is written very well, but it kind of hides some of what I think are the most important parts. Anyway, the evaluation happens. There is a probability assigned to this child to be able to reproduce. In other words, if it does like kind of okay, it might get like a 10% chance of reproducing in the next generation, where the one next to it, if it did really, really well, is given like a 70% chance of reproducing in the next generation. So it could be selected with a much higher probability, but these guys, even if they perform poorly, still have some chance of being pulled into the next generation. And that's the important part. So my question as I was reading this, is there evolutionary pressure outside the task results? I don't believe there are. I think it's just the task results at this point, although you could imagine a more broad-based sort of evolutionary pressure. In other words, a filter of what is good enough versus what's not. And then the really interesting problem here that I see is there a form of sexual reproduction like in genetic algorithms? So if you look at traditional genetic algorithms, oftentimes they have binary outputs, in other words, strings of ones and zeros. So you could imagine like disease prediction or something like that. It's like, I've got this symptom, I don't have this symptom, I have this symptom, I don't have this symptom, I don't have this symptom, right? So you give it like 64 symptoms or something, right? So it's just ones and zeros, you have it or you don't have it. And then that has to predict what the disease is. This is a traditional genetic algorithm. What you do is you randomly initialize a population of maybe 100 or 1,000 of these relatively simple AI models, and they predict the disease that's going to come out of these symptoms for a number of different diseases and a number of different symptoms. Then you evaluate these things and you're like, well, how did you do? How did you do, right? And based on their performance, and it's going to be random at the beginning, but some are going to be better than others, you assign a probability of them reproducing in the next generation. But then the crucial part is that you can take 2 of these parents and you can combine them together in whatever sort of creative way you want to. These models can basically sexually reproduce. Then you add in a mutation probability of just randomly adding or subtracting some code basically from the model, and those things produce a child. What I'm not seeing here is that sexual reproduction. I'm not seeing 2 models, 2 agents able to come together and create a baby agent. They're all sort of individual and they're pulled out. And I think that's a definite area for future research, is allowing the 2 of these children to combine and see what kind of thing comes out of them if they're able to combine. Now, does that make it much more complex to run this experiment? Heck yeah, of course it does. But I think it would be much more interesting. And I have a feeling when we look at this graph down here, I'm going to skip ahead. I can tell that I'm not going to read this paper very thoroughly at this point. So I'm sorry, I'm just like too into talking about the ideas and I'm not going to read through it. I think that's okay because other people can read the paper. You can read the paper. But anyway, when we look at the results, you can see that they're doing really, really well. The blue line is the DGM here. And you can see it makes these big evolutionary strides as it goes on, both for the SWE-bench and also for the polyglot test. The polyglot test is more interesting because it's not part of the training data set. SWE-bench is more than likely part of Claude's training set, so it kind of already has an understanding of that, but Polyglot almost definitely is not, and it makes really big improvements. In fact, it's better than the baseline by a lot. This is the baseline, the purple dash line here. You can see it doesn't quite reach the baseline of like an open source agent here and Swebench, but on Polyglot, it definitely does. But anyway, you can see it flatlines after a certain point. It gets up to, 40%, something like that. That's the best that it can do, and about 50% for Swebench. So there is definite room for improvement, and my thinking is that sexually reproducing these agents in some way, allowing them to come together and redo their tools in a, I don't know exactly how sort of manner, that's something for future research. And if anybody's interested in pursuing this, I would totally love to do a paper on this, by the way. So if you are, hit me up here or on X or whatever. But anyway, we could talk about that. But I think adding sexual reproduction and a population at the beginning would really improve the results and allow these to do even better. That's my thinking about this. And that's why I said at the beginning, this is like step one in a 10,000 step journey. It's just the beginning of how to do self-improving AI. So anyway, I'm going to skip over a whole bunch of stuff. I will mention Schmidt-Huber here, who's relatively famous, made the original Gödel machine back in 2007. Again, it's mathematical. It's not very practical, but from a theoretical standpoint, very interesting that you can create something that can provably improve itself. It's just, you can't do it practically. Anyway, the DGM here is self-referential, self-improving. That's the important part. So it's self-improving. In other words, it can rewrite itself. It literally can go in there and change its tools. It can rewrite that kind of stuff. And self-referential means that it's actually trying to solve a problem with those tools. So it's rewriting the code that's trying to solve the problem. And the upshot of this is that it not only gets better at solving the problem, but also at the same time gets better at writing tools. It gets to be a better tool builder as it builds tools to solve these specific problems. And again, as they note here in this highlighted thing, training foundation models is computationally intensive and would introduce substantial additional complexity. So they haven't done that at this point, but the ultimate, real unlock to this would be if it could rewrite its own brain. In other words, it could go in and it could look at its billions of model weights, and it could change those model weights based on what it's looking at right now and create new populations. But, we're talking about tens of millions of dollars to do training runs and things, and even fine tuning is very, very expensive. So this becomes like really, really intense kind of thing to do, but that would be the true unlock. If it could not just adjust the tools around it, but actually rewrite its brain, rewire its brain, that's the kind of thing that would allow an insane unlock. That's the real hockey stick. Right here, what we've got is we've got improvement, 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 and this is kind of a little moment at the beginning of that inflection point about self-accelerating improvement, and that's the beginning of the big unlock, but it's just the inflection point. But if we can get it to be able to rewrite its own brain, change its own weights, that's when it just goes pew to the moon. And I just want to call this out down here. A key assumption is that an increase in performance on coding benchmarks, in other words, doing better on benchmarks, indicates better coding capabilities and hence better ability to self-modify and self-improve. That's a pretty big assumption. It's not necessary that that's true, but it looks like it actually is. So what that means is as it does better on the benchmarks, it's actually becoming a better coder. It's like you imagine if, the first day that you coded in Python or something, you sucked at it, right? You didn't know what you were doing. And as you work on it for weeks and months and years, you get better and better and better at writing that code. It's that kind of a thing. You become a better programmer as you do the tasks and improve your ability to solve problems. And then what they call open-ended research, which means that it maintains an archive. It remembers the generations. It's able to pick out a previous model and look at it, even if it was suboptimal, which can lead to breakthroughs down the line that were not obvious at the particular time, which means you can bump yourself out of a local minimum again, and you can get to the true minimum, or at least closer to the true minimum than you were before. And again, they specifically call out the self-accelerating trajectory. In other words, it's not just getting better, but it's accelerating it getting better. Because if it can loop back on itself and take out the human being, this thing can just go crazy, right? It could go vertical really, really quickly. Because again, what happens when that occurs? You don't want this thing going out of control and not being aligned with what humans want, because it could get very, very smart very, very quickly at that point. So then we get into related work about open-endedness, meta-learning foundation model agents, self-improving AI, etc., etc. Again, back to self-accelerating. Then we get to the DGM, the Darwin Gödel Machine. As they state here, the DGM relaxes the Gödel machine's impractical requirement of theoretically proving that a change will improve the system, instead requiring empirical evidence from experiments to demonstrate it. So what they're giving up is proving that these things are doing better. What they're doing instead is just looking at performance on benchmarks and saying that's a good enough proxy for proving it. We're not going to prove it, we're just going to indicate it, right? It could be wrong, it might be wrong 1% of the time, but it doesn't really matter because, again, you're pulling from a population, so as long as it's right almost all the time, it's going to be fine. So then, of course, they talk about self-referential, self-improvement of coding agents. Again, it's able to refer to itself, it looks at its own tools, able to rewrite them, and then it's able to test itself and look at how it does on these benchmarks. And then we have population-based open-ended exploration. They didn't do a great job of explaining this, but there is a filter, and the filter is a pretty basic one. If the code doesn't compile, if it's not able to be run with the new generation, then it's cast out. It's not available to reproduce in the next generation. And then they talk about comparing the DGM against two baselines, which is number one, the DGM without self-improvement. In other words, it's not able to change itself, only able to change the tools, like kind of in the next generation, basically. And DGM without open-ended exploration. In other words, it's not able to keep its previous generations and pull from them. It's only kind of a one-shot deal where it goes down the line and tries to improve itself, but it's not able to pull from a population. So both of those things don't work as well as the combination of both, as we will see from the graph. And then as for the setup, it's a single coding agent to start with. So the generation starts with just a single coding agent. Again, I think a population would have been better, but expensive here, right? This initial agent is built around a foundation model and is augmented with tool use capabilities. The FM autonomously determines its action. In other words, it thinks and does whatever the next stage is and all of that kind of stuff, using whichever tool it deems appropriate. The FM has access to two tools in the initial agent. That's all. A bash tool for executing bash commands, in other words, terminal commands, and an edit tool for viewing and editing directories and entire files. And then, of course, it's able to modify those, add to them, things like that. The agent receives a single input prompt that specifies the location of the target repository, the problem statement, and the repository's testing framework. And then they run it for 80 iterations, generating one new agent per iteration, with 2 iterations running in parallel for SWE-bench. I guess they just, I think they're just parallel. I don't think they cross over each other, and 4 for polyglot. And so skipping over a lot of the experimental setup and all of that kind of stuff, again, you can read the paper. We get back to these two graphs, and you can see that the DGM without open-ended exploration, in other words, it's not able to refer to earlier versions of itself and potentially pick those out, does pretty poorly down here. That's the yellow line. It improves, but it doesn't improve very much. The DGM without self-improvement, in other words, it's not self-referential at that point, does better. It's the green line here. And so you can see it actually does okay, but it flatlines and just never able to improve. Here you can see the same thing with polyglot. And remember again that polyglot is not in the training data set for these foundation models. So you're going to see much lower performance over here, but this indicates a real improvement that it's able to do as well as it is. And there is a little improvement at generation 75 or so. So it's not completely dead-ended, but pretty dead-ended. And then when you combine both of those, of course, you see with the blue that we get big evolutionary jumps right here, like generation 21, 22, 23, 24. There's a big jump in the model over those generations, and then smaller jumps, and then a pretty big jump around generation 65 or so. And then on the polyglot test, same thing. You get these big jumps, flat lines, big jumps, flat lines. And the reason why you're seeing flat lines is because some of the best solutions later are actually operating less than the best solution at the current time. And the best solution is just evaluating on these benchmarks, right? It runs some SWE-bench tests. It's like, how well did it do? Oh, it did this well. This is the best model we've got right now. It's doing about 42% solution and everything. And then all of a sudden it jumps up to about 43, 44. Then it jumps up to 50. Anyway, it improves and improves. And that's why we're seeing kind of flatline, because there's stuff going on under the hood, but you're not seeing it until it actually exceeds that best mark. And this figure 3 is very important. So you start off with a single agent up here that's given 2 tools basically, right? And I said eventually there's a population, but it's a bit inbred, so LOL, right? Because there's no sexual reproduction or anything like that, and it just starts with 1. But anyway, it produces these other generations, and these red ones are dead ends. These are the ones that didn't compile. They just weren't good enough. So you can see it created 8 new agents from the first generation, and then from generation 2, which was able to work, it generated several more. Then on agent 3, it generated 4 more, half of which didn't work, and the other half produced, ones that didn't work. So that didn't go very far. So these are like evolutionary dead ends, if you might imagine something like that. And then we get the one that actually worked. We've got, the fourth model, which then went to the 20th model, which went to the 24th, the 47th, the 56th model, and that was the one that ended up being the best. And then if we transfer over here to the right-hand one, you can see what's going on is that the model here, this black line is this black line here. It's tracing it through the generations. And so you can see exactly what the importance of being able to pull from models that don't look like the best model at a given time, why that's important. Because you can see that the blue, sort of light blue thing here is the general. That's like the average population's abilities. And you can see that this model did substantially worse than that in generation maybe 4 or 5 or something. It did much worse. And it took a while before it got better here. And then all of a sudden it jumped up and became the best model. And then it was not the best model anymore for a little while. And then it became the best model. And here they call out what it did at those generations that caused it to be less good or more good. So at this stage, it was non-empty patch validation and retry. Then we get to more granular file viewing via lines. So it's able to view the files, not as entire files, but just as individual lines that it's looking at. Then we get a big improvement, which is more granular file editing via string replacement. So rather than having to replace an entire file worth of strings, which can lead to errors and things, it's able to go in and find an individual string and replace that. Then we got auto summarize, on context limit, multiple patch generation and ranking, which actually made it worse for a while, but then it got better. And then history aware patch generation and ranking. So these are the improvements that it made as it went along. But the really important part is that it did worse than the average for a while. Then of course it did, better than the average, much better than the average, but worse than the leading model for a period of time. And then it jumped up. So that is the advantage of doing the scientific method of being able to pull from previous generations, and B, the sort of Darwinian evolution of a generation doesn't have to be the best all the time. It's able to sample from various models and pick out ones that might be a little suboptimal at the moment, but they could prove to be better in the next generations. And then as a really quick, interesting side note, they were able to transfer between foundation models. So in other words, they were able to go from Claude 3.5 Sonnet to 3.7 Sonnet or O3 Mini or something, and they were still able to see a lot of these improvements, which means that this self-improvement, this self-referential tool building and stuff is not tethered to an exact model. It's able to transfer across to other ones. There is a slight, de-improvement. It doesn't do quite as well with these new models, but it's still very cool that it's able to transfer. That means it's a more general solution. It means the agent is thinking about things from a more conceptual level, not just a syntactical level. It's thinking strategically, not just tactically. Then we get to the all-important safety discussion. They say that, they took a lot of steps. All agent execution and self-modification processes were conducted within isolated sandboxed environments. In other words, they couldn't get out, limiting their ability to affect the host system and thereby mitigating the risk of unintended actions. Each execution within the sandbox is also subjected to a strict time limit, reducing the risk of resource exhaustion or unbounded behavior. And of course, they kept the agents to only improving their own code within a very, very limited domain of trying to solve these benchmark problems. And very importantly here, they say, at this stage, we have found no evidence of harmful or malicious behavior. So it's not trying to escape, it's just doing its thing. So that's actually a good sign at this point. And then we get to the conclusion and the limitations. The big takeaway from this was, again, what I front loaded at the beginning, which they should have done themselves. But it takes about 2 weeks and incurs significant API costs to do a single run of the DGM just on Swebench. So they had to do the same thing for Polyglot, etc. So you're talking about a lot of costs because it's a huge number of API hits to Claude Sonnet to be able to do this as it's working. And 2 weeks worth of it autonomously working is a big chunk of human time, right? It's a lot of computer time, a lot of computer cost, a lot of human time. So that's a big limitation on this. It's going to keep it from self-accelerating like crazy because at this point it's so cost prohibitive, both from actual money and from time as well. But to get back to what I said at the beginning, this is step 1 in a 10,000 step journey. This is the self-referential, self-improving, self-accelerating AI. It's just the very, very first step. It's a very small step. It's not as big as people are making it out to be because of the time and expense limitations, but it's a really, really cool first step. Are there numerous things we could do to improve this, to look at future work? Absolutely. There's a ton of stuff that could be done. And if you start thinking about large companies like Google or Meta or someone that has a lot of money to throw into this, and of course they can throw a lot more compute resources at it, you could see this, a population of these these agents rather than a single one at the beginning, sexual crossbreeding, and the ability to, modify its own brain, to modify the foundation model as it's going, those would be gigantic unlocks. Can they be done even with the biggest server clusters that are out there right now? That is an unknown at this point. But if that can be done, that is just a gigantic unlock. These things could accelerate so quickly that we really could be at that hockey stick moment where we just see self-improving AI happen within days or weeks rather than years. Alrighty, folks, that's what I've got. I really did geek out on this paper. I loved it. I hope you enjoyed coming along for the ride with me and you kind of understand what's going on. Definitely let me know in the comments what you think about all of this. And while you're down there, if you don't mind liking the video, it really helps out because it helps other people to find the video. And if you'd like to see more of this kind of content, consider subscribing to the channel, and I will see you in the next video. Bye-bye.